last week we built a gas turbine model and it looks similar to what we have here on the screen. And today we are going to continue with the simulation and model a heat recovery steam generator. And it should look similar to what we have now on the screen. It will be made of the Economiser, Evaporator, as well as the Superheater. And I'll show you how to model that in sequence. The key takeaways from this video, although there's going to be a whole lot of tips that you'll get from the video, but I need you to pay attention to the property package because we are going to set up a property package for the steam side of the process. And then we will look into how we input the process conditions, realistic process conditions. And then thirdly, we are going to look at the sequence of how we insert these unit operations into the model. Because remember, it is made up of 3 heat exchangers which are flowing countercurrent. And lastly, we will use a bit of an engineering reasoning on how we arrive at certain conclusions and assumptions. So there will be some engineering judgment that we will be applying as well. So if you are ready, go grab your popcorn, coffee, and then I'll see you on the other side. Before we get carried away, let's first do the right steps. Since we are going to be generating steam, we need to make sure we've got the right property package for the steam generation. And to do that, we go to the properties, and then we're going to insert a new property package for the steam side of the process. And you click on property package, we're going to add a new one, and I will choose the ASME Steam. This warning window comes up and says that there are a few components which are not compatible with ASME Steam. That's fine. It's going to delete those. There's only one component that is compatible, and that is water. You'll see in the component list there, it will intentionally pick up water as the only compatible component. So I'm going to rename that to water/steam. So I know that those are the components in there, and then the fluid package, I'm going to rename it to ASME Steam so I don't get confused when I get into the simulation environment. Property package all set up. We'll try to make some space here. And as I've said earlier, the way I model the HRSG is a little bit counterintuitive, but you will see why I say that. First, we'll start with the last heat exchanger, which is the Economiser. And to model that Economiser, we're going to use a shell and tube heat exchanger. That's the icon there, shell and tube heat exchanger. And one thing that I will also recommend is to change this symbol. The default symbol, because of the way the flow goes in this flow sheet, they can get all mingled up and confusing. I don't like to use these symbols for that specific reason. And to do that, I'll show you the reason why actually as we go. But you double click on it, or not double click, but right click. And then you go to change icon. And then I want to change it to this one here. This wireframe helps with the stream flows. They don't cross each other. They don't go over each other as you insert them into the unit operation. You'll see what I'm talking about. I'm going to set this as my default for now. And I press OK. So that changes the heat exchanger to look something like this. And then I'm going to double click on that, rename it to Economiser. And we don't have any streams going into it just yet. The first stream is the boiler feed water. And that's our water that we're going to be putting into the HRSG, boiler feed water. And the temperature of the boiler feed water that comes into the HRSG is 105. So that's a typical deaerator operating temperature. It's between 100 and say 105. And then this one is also a process input or process requirement. For the project that I was working on, the steam pressure was about 1000 kPa. So I'm going to use 1000 kPa as the boiler feed water pressure. And the datasheet also claims that the conditions that we've modeled earlier, this turbine should be able to produce 35 tons per hour. And here's the datasheet that shows the application performance. The steam in unfired operation is 35.2 tons per hour. That's equivalent to 35 cubic meters per hour. So we are trying to replicate that specification. So we are going to specify the mass flow rate of the boiler feed as 35 tons or 35. Now I want to use the cubic meters. Let me use the cubic meters because someone did ask, why did I use the liquid volume flow at standard conditions? And I've explained it in the comments. HYSYS does its flow rates a little bit different. There's logic to it, but it's not as straightforward. So I've attached the documentation that supports why we do it this way. So that's 35 tons per hour or 35 cubic meters per hour of flow rate. And you see it is still saying Peng Robinson. I need to change this and make it ASME Steam. And then I'm going to also change the composition. The composition is just 1, the mole fraction. That gives me a mole fraction of 1. And that line is fully specified now. I'm going to try and turn it around. Let me first switch off these process conditions, the temperature and pressure. They're making the flow sheet a little bit untidy. To rotate anything on the flow sheet, just click on the item and press 1, and it should rotate it. See, that has now rotated into this direction. So I'm going to feed this into the economizer, and the water is going on the tube side, the boiler feed water. It comes out in liquid phase. So I will call this boiler feed water to the evaporator, because that's where it's going, right? After the economizer, it goes into the evaporator. And then before you go anywhere, you come to the parameters, then you specify your pressure drops. For this project, we specified very little pressure drop on the shell side, 1.5 kPa and 2 kPa on the tube side. The tube side is where the steam is flowing, and the shell side is where the hot flue gas is flowing. And then once I do that, I will just make sure that I've got the geometry correct here. Now you can see it's starting to look a little bit untidy and confusing. I need to turn this unit operation so that the flows goes in the direction that I'm working in. So I turn this stream that way, because everything is going towards the turbine, because remember, it's a counterflow process. The steam goes towards the hot gas and the hot gas goes towards the stack. With the other icons, you wouldn't be able to see this cleanly. It just crisscrosses and it just makes a whole lot of mess. But anyhow, let's continue. So we see this blue line already tells you that there's something missing here. I'm going to tell you a trick how you input these variables, because of the only thing that you know is this temperature that's coming in here and the pressure. What happens inside the HRSG, it all comes back to engineering logic. So the pressure is already calculated. This is 998. So that comes from the 1000 kPa. We've got a 2 kPa pressure drop, and then we come up at 998. And then the temperature, we don't know the temperature, but we know that this stream is still liquid phase. We're going to force it to be liquid, right? And then HYSYS will calculate the saturation temperature. So I've got a vapor phase of 0, and then the saturation temperature is 184. So see, now it's 10 dark blue. Now I know this is fully specified. Then I can continue to the next unit operation. This is how I find the process to be relatively simple, and it's not that confusing. And then there's the second heat exchanger, pretty much the same logic. This one is the evaporator. And the tube side, what comes into the evaporator is the boiler feed to the evaporator stream that we just labeled. See what I was talking about regarding the icons? We need to spin that again. And then what comes out is, I will call this is now steam. So what happens in here? The temperature of the boiler feed does not change, but we're changing the phase. This is where we start to generate the steam in vapor phase. Right, so I'm going to call this saturated steam to the superheater. So we've got steam now in vapor phase and it's going to the superheater. That's our outlet stream. And then before you go any further, you come here to the parameters, you specify your pressure drops. Pressure drop in the shell side 1.5, pressure drop in the tube side 2 kPa. And it still says requires a feed stream. That is the hot gas stream that we still going to come back to. So let's spin this. I'm clicking on it and I press 1 to rotate it. And then we need to specify the conditions on this side, right? What did we say? The temperature coming in here is 184, the saturation temperature. And the steam comes out still at 184, but it has changed phase. It is now vapor. So what do we specify here? We're going to say, okay, what is our temperature? We can specify the temperature as 184 because we know that that is the saturation temperature. You can see that it is still vapor. On this side, it was liquid. Now it's vapor. Everything is in vapor phase and at 184. So the evaporator is half specified in terms of the steam flow. So you see, I'm doing the steam flow up until we get to the superheater. And I'm going to repeat the same process for the superheater. Double click, rename, and then this is the superheater. The inlet stream is the saturated steam to superheater. And then now here we will have superheated steam to the steam header. And before you go any further, you go and specify the pressure drops, 1.5 in the shell side and 2 kPa on the tube side. And then you press enter. And then we do that trick again. We are going to rotate that, and here we are. But we still need to specify the outlet conditions of the superheated steam. For this project, because of the steam was used for process heating, so there was no really need to superheat the steam. We only superheat the steam, just a small fraction, to make sure that it doesn't condense in the header or as it goes towards the end users. I'm just going to tell you what this steam was used for. It was for a tissue making process, and the steam was used in the Yankee dryers. And in the Yankee dryers, you do not need superheated steam. You just need saturated steam to heat the process. So now that that's out of the way, you kind of know where this process was actually applied. We're going to specify the outlet conditions of the superheated steam. And we know the saturation temperature at 1000 kPa is 184. So we're only going to superheat this by 5 degrees, right? So I'm going to specify the superheat temperature at, say, 189. And you press enter, and then the whole steam is specified. Now we need to put in the counterflow of the hot gas. I'm going to double click the hot flue gas, and that is going in the shell side. You can come to connections, and then the inlet stream is that one there, the hot flue gas. I don't know why I hit it. That's hot flue gas. Boom, and there it goes in there. And then the outlet will be hot flue gas going to the evaporator. And by just doing that, you can see that unit operation has converged, right? So we've fully specified that it should be green. There we go. Now we've got this stream going into the evaporator. I will double click on that, go to connections, and what is the, it is, I named it to hot gas to evaporator. That's our inlet stream that goes into the evaporator. Hot flue gas to the evaporator is the inlet stream, and what goes out is hot flue gas going to the economizer. And that also converges, no mucking around there. And then lastly, we do that for the economizer. Double click, connections. What's the inlet in the shell side is the hot flue gas to the economizer. What goes out is it's not hot anymore. I'll call it just flue gas. to the vents there. Enter, and that also converges. So we've got all this all sorted. Now, in the true sense of this project, we've already simulated the HRSG. There's a few things that we might want to optimize on, like putting in a steam drum here and also recycling some of the steam back into the superheater. We didn't have that in our system. However, I reckon it is important that I show you how that is done. That will be in the next video that I will be doing. That shouldn't take too long. Now, with this flow sheet completed, we need to do a comparison of what the data sheet tells us versus what we have modeled. This is how you simulate the HRSG. Simple, easy, non-confusing. At least that's how I feel. I will show the temperature and pressure of the streams. It gets a little bit messy. That's why I ended up doing this. And I will also toggle the line breaks just to make them all straight up. This is toggle the line breaks. So in summary, what we have is our boiler feed at 105 degrees. The boiler feed goes into the economizer. It comes out just at the saturation temperature. At this temperature, it is just about to boil. And then we put it into the evaporator where it starts to boil. We are changing it from liquid phase to gas phase, which is the latent heat of vaporization. The temperature remains the same. It's 184. And once we've got all the steam now in vapor phase, we go into superheat that steam by 5 degrees from 184 to 189. And that's our steam that goes to the header at a pressure of 994 kPa. I hope that makes sense. If it doesn't, let me know, and then we can drill a little bit deeper into those comments. Now, one other thing that I wanted to just show, this is just cosmetics, this is really not engineering as such, but if you're going to produce a flow sheet like this for someone, you probably want to make sure that they can see and follow the flow sheet nicely. Normally what I'll do is to distinguish between the steam line and the vapor line or the gas line. I would just do this, right click on the stream, right click, and then so draw wireframe or draw thick streamline. This is just me being pedantic, but yeah, this is how I like to do things. So we've got the steam being produced at this mass flow rate. I'm going to add the mass flow rate here. Mass flow. We'll call this steam production rate. And you can see that's 35 tons per hour, or 35,000 kilograms per hour. And that is pretty much close to what the datasheet actually says. I hope this made sense. I will continue with the lessons, because you can see the more we develop this flow sheet, the more detailed it becomes. And the scope doesn't end there. This is just the framework. There's also steam drums that we can put in. There's also recycle loops that we can put in there just to make sure that we've got a full-blown flow sheet. Because this superheated steam, it goes and gets used in the Yankees and all that. And then it recycles back as the boiler feed, pretty much a closed loop. And then within that loop, there are some makeup streams and bleed offs. We can go ahead and model those, but those are not really the scope of our videos. And I just wanted to show you how to do the turbine and HRSG. And then once we've done that, we are going to, as I promised, we are going to change the flue gas and start to inject hydrogen at up until 20% and see how it affects the turbine and how it affects this part of the process. Because remember, there are two things happening, or a couple of things happening really. This heat exchange happening in the superheater and the evaporator and the economizer is dependent highly on the composition of the hot flue gas. And if we're putting in hydrogen, this composition changes. We need to know how it's going to affect this, the heat exchange there. And the last thing is, see, we've got the flue gas going to the vent. This flue gas is at 183 degrees. In the project I was working for, it was about 185, which is pretty close. But it has a dew point. And this stream always has to be above the dew point, because of if the temperature drops below the dew point, you start forming condensation in the stack. And once you start having condensation in the stack, corrosion will start. It will start having blockages, things that you were not prepared for, or things that the system was not designed for. Just a quick side note before I wrap up this video, I'll just show you the current dew point of this stream. I'll go there, I'll just double click on it, and then we go to properties, and we can check the water dew point of this stream. Where is it? There's the bubble point. If you can't see it here, we can add it and then come here, go to the gas, and then there's the water dew point. Apply, add it to the list. You can see this, the dew point of the stream is currently 36. So any temperature above 36 is good, because of everything remains in vapor phase. But when we start putting in hydrogen as part of the fuel gas composition, that dew point will start to increase. And we need to make sure that whatever temperature that comes out here is above the dew point. That will be one of the things that we study as we continue with this series. I hope you had some fun today, and we'll continue to build up on the knowledge. Let me know what you think in the comments, and I will see you on the other side. Cheers for now.